August 1943. A typhoon hits a U.S. military base in the Pacific. Wind speeds reach 150 miles per hour. When it's over, every wooden barracks is destroyed. Roofs torn off. Walls collapsed. 300 soldiers without shelter, 6,000 miles from home. But one type of building stands untouched. Not a single panel damaged. A curved steel structure that looked ridiculous. Engineers said it would fail. It didn't. This is how the Quonset hut survived what nothing else could. When America entered World War II, the military needed bases across the Pacific immediately. The standard solution was wooden barracks. Simple, fast to build, familiar. The problem was the Pacific environment destroyed them almost as fast as they went up. The tropical heat and humidity rotted wood in months. Termites consumed support beams from the inside. Buildings that looked solid would suddenly collapse. Maintenance crews couldn't keep up with the decay rate. Then came the typhoons. Pacific storms with sustained winds over 100 miles per hour. Rectangular wooden buildings acted like sails. Wind would catch the broad side, connections would fail, and entire buildings disintegrated. During one typhoon in 1943, a single base lost over 200 buildings in hours. The shipping problem was just as critical. Every piece of lumber had to be shipped thousands of miles across submarine-infested waters. Cargo space was desperately needed for ammunition and fuel. The military needed buildings that required minimal shipping volume, could be assembled in hours by non-experts, and could survive typhoons. The specification seemed impossible. Enter engineer Peter Mellon at Quonset Point Naval Air Station. His solution was radical. Instead of fighting wind with a rectangular structure, build a half-cylinder. A simple curved arch of corrugated steel anchored directly to the ground. No separate walls and roof, just one continuous curve. No complex framing, the corrugated steel provided all the structural strength. Military architects hated it. It looked like a drainage pipe. The curved walls meant lost usable space. The all-metal construction would be blazing hot in summer. The design was too simple. Surely something so basic couldn't work, but Mellon understood physics the architects missed. The half-cylinder presents minimal surface area to wind from any direction. Wind hitting the curved surface deflects over and around instead of catching and pushing. An arch converts loads into compression forces along the curve, which steel handles perfectly. The corrugations add rigidity preventing buckling. The entire structure acts as one integrated unit with no weak connection points. The shipping efficiency was revolutionary. A complete 20 by 48 foot Quonset, big enough for 15 to 20 men, packed into a space the size of a pickup truck bed. Compare that to the lumber volume for an equivalent wooden barracks. A crew of 8 non-specialists with basic tools could erect a complete Quonset in under 8 hours. No welding, no heavy equipment, no skilled carpentry required. The real test came during typhoon season 1943. Bases now had a mix of wooden barracks and Quonset huts. When typhoons hit, the results were undeniable. At one base in the Philippines, a typhoon with 140 mile/hour sustained winds hit directly. Every wooden building was destroyed or severely damaged. The Quonset huts remained standing. Not just standing, virtually undamaged. A few panels had minor dents where debris struck them. That was it. Troops who'd been housed in Quonsets rode out the storm inside. Troops in wooden barracks had to evacuate to shelters. The physics are straightforward. At 140 miles per hour, wind pressure is roughly 100 pounds per square foot. On a rectangular building with a 40-foot wall, that's 40,000 pounds of force trying to push it over. Wooden connections pull out under that stress. The Quonset's arch shape means wind pressure creates compression forces that push the structure down into its foundation rather than trying to tip it over. The structure gets more stable under wind load, not less. There's a documented case from Okinawa. A Quonset took a direct hit from debris during a typhoon. A large piece of wooden building launched by wind struck at high speed. The debris punched through one corrugated panel. That single panel dented, but the structural integrity was unaffected. After the storm, a crew replaced that panel in 20 minutes. The building was immediately back in service. Compare that to wooden barracks with even minor damage. If wind tore off part of the roof, water would pour in. The building would be uninhabitable until major repairs were completed, taking days or weeks. A Quonset could take significant damage and remain functional. By 1943, the Quonset had proven itself so thoroughly that the military scaled up production massively. Between 1941 and 1946, over 170,000 Quonset huts were manufactured. They shipped to every theater: Pacific Islands, North Africa, Europe, Alaska. They served as housing, hospitals, mess halls, workshops, warehouses, and aircraft hangars. The cost efficiency was remarkable. A wooden barracks cost $1,800 in 1943 and required constant maintenance. A Quonset cost $1,300, required virtually no maintenance. Lasted far longer, and could be disassembled and reused. Over its service life, a Quonset cost perhaps a quarter of traditional construction. When the war ended, the military sold tens of thousands as surplus. Veterans who'd lived in them during the war bought them for homes, workshops, and farm buildings. A veteran could buy a surplus Quonset for a few $100s and erect it on his property in a weekend. The post-war housing shortage made the timing perfect. Here's what's remarkable: Quonset-style buildings are still being manufactured today, 80 years later. Modern versions use improved materials, but the curved arch shape persists because the physics that made it work in 1941 are still valid. They're used for homes, warehouses, workshops, farm buildings. The prepper community loves them. The tiny house movement has embraced them. The military architects who criticized the design for being too simple missed the entire point. The simplicity wasn't a flaw, it was the genius. Fewer components means fewer failure points. Simpler assembly means less room for error. Basic geometry means the physics work reliably regardless of conditions. The Quonset hut saved countless lives during World War II by providing shelter that didn't fail when everything else did. Troops who slept safely through Pacific typhoons while wooden buildings disintegrated around them understood the value. And that value continues today. Sometimes the best solution really is the simplest one. Sometimes the design that looks wrong turns out to be exactly right. And sometimes an engineer with 60 days and an impossible problem creates something that lasts forever.